Hello, my name is Kristen Stecker, and this is my Acoustics 1 final project presentation. The purpose of this project was to read and analyze the article, Spatial Ultrasound Modulation by Digitally Controlling Microbubble Arrays. In this article, spatial modification of the phasor amplitude in an acoustic ultrasound wave was studied to determine an accurate method for dynamically reshaping incident plane waves into complex images. This is a technique that utilizes a large number of acoustic sources, which can be tuned to generate complex and dynamic wavefronts. In this article, a newer method for producing acoustic ultrasound images is presented. A medical ultrasound is a procedure which uses high-frequency sound waves to produce an image of an internal body part. Ultrasound imaging is performed by the propagation of compressional waves and recording the successive scattering induced by acoustic impedance mismatches. Currently, there are sophisticated techniques that can be used to detect and analyze ultrasound waves, but these technologies are still fairly basic. The idea of having the capability of projecting changeable patterns or images is desired. Specifically, this would be very useful in searchable applications. Some other applications would include biomedical ultrasounds for monitoring an unborn child, detecting cancer, acoustic energy transfer, industrial sensing, and particle manipulation. Present ultrasound imaging methods have limitations on the amount of particles that can be used in the application, and often may require utilizing highly symmetric arrangements. Phased array transducers are limited to using less than 1,000 pixels, which is well below the required amount of pixels for controlling ultrasound waves. The authors propose a new method for generating images out of sound waves through a dynamically spatial ultrasound modulator, also known as SUM. SUM can generate binary amplitude transmission holograms by utilizing 10,000 active elements through a CMOS chip, where each element has the ability to be controlled to form microbubbles through electrolysis. These microbubbles can be set up in patterns to produce predefined images. The principle of SUM through microbubble arrays requires binary amplitude modulation of the microbubble pattern as an acoustic hologram, which consists of pixels with an amplitude of either 0 or 1. The transducers are turned on, which transmit an acoustic wave through the SUM, which are blocked at pixels which contain a microbubble. The wavefront that still remains propagates into the upper container and then diffracts, which forms a target sound pressure distribution. Microbubble patterns are pre-calculated as a binary amplitude acoustic hologram. Optimization of the binary amplitude hologram is done by the iterative angular spectrum approach. For this concept, in the hologram plane, the phase distribution is converted into a binary amplitude distribution with a fixed phase at each step. From the propagated target image, an average phase value can be determined. The amplitude of the hologram pixels are then set to 1. This demonstrates that SUM can be used to project changing acoustic fields. From the work, it can be finally concluded that SUM allows for the generation of binary amplitude acoustic holograms. Microparticles in predefined shapes can be generated into projected acoustic fields. The projected acoustic fields can be updated and used to assemble microparticles into predefined shapes. Instant acoustic plane waves can be spatially modulated by using pattern of microbubbles, which produces a complex wavefront. This work demonstrates the first parallel assembly of microparticles using a dynamic spatial ultrasound modulator.